Hey everyone, and welcome to The Explainer. Today, we're taking a cinematic journey through the absolute bedrock of modern technology. We're going to explore the 8 revolutionary milestones of desktop CPU architecture. Now, we aren't just looking at boring, incremental updates today. No, we're looking at the fundamental, mind-bending leaps in engineering that literally changed computing forever.
But real quick before we get going, let me ask you a question. Did you know that the processor powering the computer you're probably using right this second still speaks a digital language that was invented all the way back in 1978? It's kind of wild to think about. Every single day, we instantly open dozens of browser tabs, stream 4K video, play these massive photorealistic games. But behind the scenes, it is the result of one continuous, decades-long battle where brilliant engineers constantly had to overcome massive physical bottlenecks just to keep progress alive.
Okay, let's dive right into this. Our roadmap for today will take us through 5 distinct eras of computing breakthroughs. We're going to start with the birth of x86, move into breaking the memory barrier, explore the multi-core revolution, then we'll look at chiplets and hybrid computing before arriving at our current frontier, the AI desktop era. So, Section 1. The birth of x86. Let's look at the very first major bottleneck. You see, before 1971, if you wanted a computer, you were looking at a massive, room-sized machine built from hundreds, sometimes thousands of completely separate components. But then, Intel drops the 4004. And this chip sparked the absolute birth of miniaturization. It proved once and for all that an entire CPU could actually fit onto one single piece of silicon. But the real turning point, that arrived in 1978 with the Intel 8086. And the concept of x86 is absolutely crucial to understand here. You can think of x86 as the fundamental digital alphabet and the grammar rules that a processor uses to actually understand software. The 8086 laid down this foundational language, and it quickly became the absolute industry standard for personal computers. But, as revolutionary as it was, it had a glaring problem. It relied on a 16-bit digital highway. And as software got more complex with early graphical interfaces, that narrow highway started to completely choke.
So, traveling forward on our timeline to the mid-1980s, engineers desperately needed to widen that digital highway. They needed hardware capable of running rich, modern operating systems.
Which brings us right to 1985 and Section 2, breaking the memory barrier. Intel stepped up to the plate with the legendary 8386 processor. By moving from 16-bit to true 32-bit computing, the 386 literally doubled the width of that data highway, delivering roughly twice the performance of those older chips.
But the 386 was a massive game changer because it introduced something called virtual memory. Imagine your computer's RAM is a physical office desk. Before virtual memory, if your desk got totally full of paper, you had to stop working completely. The computer would just crash. But with virtual memory, the CPU seamlessly uses your hard drive as this infinite imaginary filing cabinet working right behind the scenes. Without this specific architecture, the modern multitasking we all totally take for granted in Windows and Linux simply wouldn't exist.
Now, even with this wider 32-bit highway, the CPU was still kind of acting like a single toll booth operator, just processing one instruction at a time. To go faster, it needed to evolve again. In 1993, the Intel Pentium architecture introduced superscalar execution. This meant the CPU finally had multiple execution units working in parallel, allowing it to process multiple instructions at the exact same time.
Then, the subsequent Pentium Pro took this a massive step further with out-of-order and speculative execution. Think of it like a genius restaurant chef. Instead of just taking one order, cooking it, and waiting around, this chef actively analyzes the line of customers. They predict, hey, 3 people are probably going to order fries, so they start cooking the fries early. If they guess right, the food is served instantly. If they're wrong, they just toss it out. This highly clever architecture resulted in a staggering 30 to 50% improvement in instructions per clock, or IPC.
Fast forward a bit to 2003, and the industry faced an epic showdown. That 32-bit highway from 1985, well, it had hit a wall. It could only access 4 gigabytes of RAM. And while Intel tried to introduce this proprietary, completely incompatible 64-bit system, AMD swooped in and struck absolute gold with the Athlon 64. AMD elegantly expanded the existing x86 language to support 64-bit, making it perfectly backwards compatible. Plus, they physically cut out the memory middleman on the motherboard, putting the memory controller directly inside the CPU itself. This smarter engineering utterly destroyed Intel's reliance on just brute-forcing raw clock speeds.
Pushing forward on our timeline to 2006, we hit a genuinely dangerous physical limit. Intel's obsession with pushing those raw clock speeds higher and higher was literally melting processors. Enter Section 3, the multi-core revolution. In the mid-2000s, there was a very real thermal crisis happening. Processors were essentially acting like space heaters on your desk, and laptop batteries were dying in a matter of minutes. Engineers had to figure out a way to stop blindly increasing megahertz.
Intel finally realized the solution wasn't just building a single boiling hot core, so they released the Core 2 Duo, totally abandoning the megahertz race. By focusing entirely on efficiency, the Core 2 Duo drastically lowered power consumption while somehow delivering up to 40% higher instructions per clock than the old Pentium 4. So the really crucial point here is this. Instead of revving one single engine right up to its breaking point, you now had two highly efficient workers sharing that massive load. This breakthrough is what allowed your PC to seamlessly run a background virus scan on one core while you gamed flawlessly on the other. It created the definitive blueprint for the next entire decade of computing.
But as we slide the timeline forward from 2006 up to 2017, a brand new, somewhat hidden bottleneck emerged. To get more power, companies tried building these massive chips with 10 or more cores, but manufacturing giant, single-piece silicon chips, which we call monolithic dies, was becoming astronomically expensive. Literally, just one microscopic defect on the silicon meant the entire chip went straight in the trash. Progress essentially stagnated.
But that stagnation was completely shattered in Section 4, chiplets and hybrid computing. AMD made this absolutely ferocious comeback with their Zen 2 architecture, fundamentally changing how silicon is manufactured from the ground up.
They introduced what's known as chiplet architecture. Imagine perfectly snapping together tiny, hyper-powerful Lego blocks. Instead of risking a large, incredibly expensive single chip, AMD manufactured small, cheap, highly reliable silicon clusters and then just stitched them together using an exceptionally fast connection. This brilliant move drastically lowered manufacturing costs and allowed them to bring massive 16-core processors to mainstream desktops at prices people could actually afford.
But here's the catch. Having 16 identical high-power cores wastes a ton of electricity if you're just, reading a PDF. So in 2021, Intel responded with their Alder Lake architecture, bringing hybrid computing directly to the desktop. Think of it kind of like a hybrid sports car. You have an electric motor for efficient city driving and a massive V8 engine for the open highway. Intel's Thread Director acts as a really smart transmission. It assigns the heavy lifting, like 4K video rendering, to large, performance cores. Simultaneously, it moves simple background downloads to highly efficient, almost zero power efficiency cores. It flawlessly balances raw muscle with marathon endurance.
Taking one final jump on our timeline brings us right to the present day. And what is so fascinating here is that the very metric of what makes a processor good has totally shifted away from just raw clock speed.
Welcome to the absolute frontier. Section 5, the AI desktop era. Modern processors, like the Intel Core Ultra 200S and the AMD Ryzen AI series, well, they aren't just traditional CPUs anymore. They've evolved into incredibly complex system-on-chips.
Just look at how modern silicon is laid out now. Because running advanced AI models on a standard CPU just drains a massive amount of power and runs way too slowly, modern chips now integrate a dedicated neural processing unit, or NPU, right alongside the CPU for logic and the GPU for graphics. These everyday tasks we rely on, running local digital assistants, generating high-res images, blurring your background on Zoom calls, and transcribing voice in real time, they all rely on machine learning. By offloading those specific tasks to the NPU, your desktop can handle intense AI workloads right there on your desk with unbelievable performance per watt.
So when we take a step back and really review these 8 milestones, we're looking at an awe-inspiring 40-year journey. We went from room-sized mainframes and the birth of x86 to 32-bit multitasking, superscalar predicting chefs, 64-bit efficiency, multi-core problem-solving, chiplet Lego blocks, and now, these highly intelligent, power-efficient AI desk companions. It is truly one continuous, unbroken chain of brilliant engineers, each solving the absolute biggest bottleneck of their generation, just so we can boot up our PCs and effortlessly connect to the world.
So, as we wrap up this explainer, I want to leave you with a bit of a nostalgic question to think about. Take a second and try to remember, what was the very first CPU you ever owned in your very first computer? Because next time you look at the silicon sitting on your desk, I hope you remember the decades of relentless, mind-blowing innovation sitting quietly inside that tiny chip. Thank you so much for joining me on this deep dive into CPU architecture, and I will see you in the next explainer.